Okay, so today we're going deep on Avro.
Avro.
You know, it's one of those things that keeps popping up, especially in these technical interviews,
Right.
for senior software engineer roles,
Of course.
where you really got to show, like, you've thought about how data gets moved around, how it changes over time.
It's critical.
Yeah, like how do you actually build systems that can handle that kind of evolution?
For sure. And that's where Avro shines.
Yeah.
So think of this as your crash course on Avro's strengths, how it handles data, changes, why it's so powerful in these complex systems.
Okay, so we're not going to be messing around.
No.
We're going to get into the nitty-gritty.
Absolutely. We're going to dive into how it compresses data, how different versions of data structures can talk to each other.
Right, because in the real world, schemas don't stay the same forever.
Never.
Right, so let's start with the basics.
Mm-hmm.
What is Avro and what problem is it designed to solve?
So at its heart, Avro is a binary way to encode data. Instead of using text-based formats, it takes your data and turns it into a stream of bytes. Okay.
Which is way more efficient when you're talking about storage or zipping data across a network. You've probably come across other binary formats like protocol buffers or thrift.
Right.
Avro's in that same family, but it's got its own unique style. Now, the interesting part is where it came from. It was born inside the Hadoop project back around 2009.
Oh, wow.
The Hadoop team realized that the existing ways of serializing data weren't cutting it for the massive amounts of data they were dealing with.
Yeah, big data problem.
Exactly. Big data problems.
Right.
So they needed something that could scale.
So it came out of this need for efficiency and being able to handle these huge data sets.
Absolutely.
Okay, so now we got to talk about schemas, because it seems like schemas are a big deal in Avro. Why is that?
The schema is basically the heart and soul of Avro. It's like a blueprint that lays out exactly how your data is structured.
Okay.
But here's a cool part. Avro gives you two ways to define these schemas. There's Avro IDL, which is made for us humans to read and understand.
And then there's a JSON format, which is perfect for machines to parse and work with.
Oh, that's clever. So we've got a human-friendly version and a machine-friendly version.
Exactly.
Okay, so can we see an example of what a schema might look like in action?
For sure. Let's say we're working with data about people. In Avro IDL, a schema for a person record could look a little something like this.
Okay.
You'd have a record called person, and within that you define the fields. So you might have a field for username, which would be a string.
Okay.
Then maybe a field for favorite number, which could be a long integer, but we also want to allow it to be null.
Right.
And we'll set a default value of null for that field. And finally, let's add an array of strings called interests.
Okay, so we've got username as a string favorite, number can be a whole number or nothing at all, and then we've got a list of strings for interest.
You got it.
Makes sense. How would that same schema look in JSON for the machines to understand?
All right, so in JSON, it's going to look a bit more structured. You'll have this top-level object with a type field set to record to tell you it's a record definition.
Okay.
Then you'll have a name field, which in this case will be person.
Got it.
And then the heart of it is the fields array.
Right.
And within that array, you'll have an object for each field describing its name and type. So for username, the name is username and the type is string, pretty straightforward.
Right.
For favorite number, it gets a little more interesting. The type is an array with null and long inside, indicating that it can be either of those.
Okay.
And then we also have default null in there to set that default value.
Right.
And for interest, the type is another object specifying that it's an array, and the items within that array are strings.
I see. So it's the same information just laid out in a way that software can easily process.
Exactly.
You mentioned earlier that Avro was designed with efficiency in mind. How do these schemas help achieve that compact binary encoding?
Okay, so this is where things get really cool. If we take our person example, and let's say the username is Martin, their favorite number is 137, and their interests are daydreaming and hacking.
Okay.
Avro can pack all of that into a tiny little package of just 32 bytes.
Wow, 32 bytes. That is impressive.
It is right. It's significantly smaller than many other ways you could represent that same data. And this is crucial when you're dealing with large data sets or when you need to send data over the network quickly.
Yeah, that makes sense.
Yeah.
How does it manage to squeeze so much information into such a small space?
The magic is in how Avro's encoding works. It strips away all the unnecessary fluff and focuses solely on the data values themselves. It's like a super streamlined sequence of just the essential information. It doesn't bother with things like field names or explicit type tags within the encoded data itself. It's just the raw data laid out one after the other.
So it's just the pure data packed in there.
Exactly, just the pure essence of the data.
Can you walk us through how those 32 bytes actually represent our example person?
Sure thing. So the first part of that byte sequence is going to tell you the length of the username Martin, which is 6 bytes. Then it just lays out those 6 bytes representing the characters in Martin.
Okay.
Next up is an indicator for the favorite number. This tells you that we're dealing with the long integer part of our union, null long, and that it's not null.
Right.
Then you have the encoded bytes for the number 1037. After that, there's another indicator that tells you how many items are in the interests array, which in our case is 2.
2 items, daydreaming and hacking.
Exactly. Then you get the length of daydreaming, which is 11, followed by the 11 bytes representing daydreaming.
Okay.
And then the same thing for hacking, length of 7, followed by the 7 bytes for hacking.
Got it.
And lastly, there's a special marker that signals the end of the interests array.
So it's all very cleverly laid out.
Yeah.
But if the encoded data itself doesn't contain the field names or the types, how does the reader on the other end know what's what?
That's the key. The reader relies completely on the schema, the same schema that was used when the data was written, to figure out the order of the fields and the data type of each one. It's like they have this shared understanding, a secret decoder ring.
I see. So they're both working off the same blueprint.
Exactly. If they didn't have that shared schema, those 32 bytes would just be a jumbled mess.
So the schema is absolutely essential for decoding to work properly.
It's non-negotiable.
What happens if the schema that the writer used and the schema that the reader is expecting are different?
That's when you start running into trouble. If the reader's expecting a number in a certain spot, but the writer put a string there, things are going to get messed up.
Right.
You'll end up with incorrect data or errors. This is why being careful about how you manage and evolve schemas is super important when you're working with Avro, especially in systems that are constantly changing.
Which brings us to schema evolution. That sounds like a pretty critical topic, especially as systems grow and change over time.
Schema evolution is where Avro really shines. The core idea is that you have the writer's schema, which is what was used to encode the data, and then you have the reader's schema, which is what the application reading the data is expecting.
Okay.
And the beauty of Avro is that these two schemas don't have to be exactly the same. They just need to be compatible.
Compatible, but not identical.
Yeah.
So there's some wiggle room there.
Exactly. There's flexibility built in. And this is what allows Avro to handle changes in data structures gracefully without bringing the whole system crashing down.
How does Avro actually figure out how to read data written with one schema using a slightly different schema?
Okay, so when Avro data comes in to be read, the Avro library kicks off this process called schema resolution.
Schema resolution, yeah.
It takes the writer schema, which is often bundled with the data, and the reader schema, and it starts comparing them field by field.
Okay.
It figures out how to wrap the data from the writer's format into the format the reader is expecting. It's like a translation service.
I like that, a translation service.
Yeah, and Avro has very specific rules for how this translation happens laid out in the Avro specification.
So it's not just making things up as it goes along.
No, it's all very precisely defined.
Okay, let's try to visualize this.
Yeah.
Can we use our person record again as an example?
Absolutely. Let's say we have a service that's writing person data using this schema, username string, favorite number union, null long interests array of strings, and photo URL string.
Right.
Now, let's say another service needs to read this data, but it's expecting a slightly different schema. It wants user ID long favorite number union null int username string and interests array of strings.
All right, so I see some differences right away. The order of username and favorite number is flipped. The reader wants a user ID, which the writer isn't providing the favorite number, and the reader's schema is an int instead of a long, and the writer is including a photo URL that the reader doesn't care about.
You're spot on. There are a few key differences there.
So how does Avro resolve all of this?
Here's how Avro handles this situation. The username fields will be matched up correctly even though they're in a different order because they have the same name.
Oh, so the name is what matters.
The name is key.
Okay.
Now for favorite number, Avro will match those fields up as well. And it's smart enough to attempt to convert the data from a long to an int if the value will fit.
Oh, wow. So it does some type conversion for you.
Exactly. Now, the interest field, that's a straightforward match because both the name and the type and array of strings are compatible.
Makes sense. What about the photo URL that the first service wrote, since the second service doesn't even have a field for that?
Avro's just going to ignore it. It's like it never existed.
Oh, so it just skips over it?
It just skips right over it. No harm done.
But what about the user ID that the second service wants, since it's not in the data from the first service?
Ah, good point.
Yeah.
So if the user ID field in the reader schema has a default value defined, Avro will use that default value when it's reading the data.
That's smart. So it fills in the gap with a default value.
Exactly. It tries to make things work smoothly.
This is really cool. So it's all about matching the fields by name and then handling any differences in types or whether a field is present or not.
You got it. That's the essence of it.
This sounds incredibly useful for keeping systems working together even as they evolve. Are there any specific guidelines we should follow when we change our Avro schemas to make sure everything stays compatible?
Absolutely. There are some golden rules to keep in mind when you're evolving your Avro schemas. These rules are all about making sure that data can flow smoothly between systems that might be using different versions of the schema. And we call this backward and forward compatibility.
Backward and forward compatibility.
Got it.
So what are the most important things to remember when we're updating an Avro schema?
The number one rule is that whenever you add or remove fields, you should always define a default value for those fields.
Okay.
So for example, let's say you add a new field to your schema and you give it a default value. Older systems that are reading data written with this new schema, they'll just use that default value for the new field that they don't know about.
Okay, so it's like they don't even notice that the field is missing.
Exactly. It keeps things running smoothly. This is what we call backward compatibility.
Backward compatibility. What about if we remove a field from the schema?
If you remove a field that used to have a default value, older systems that are writing data with the old schema, they'll still include that field. But newer systems that are reading this data with the updated schema, they'll just ignore the field because they don't expect it anymore.
Okay.
And this is forward compatibility. So you're good on both ends.
Right. So as long as there's a default value, we can add or remove fields without causing problems.
You got it.
Yeah.
But here's the catch. If you add a field and you don't give it a default value, older readers won't know what to do with data that's missing that field.
Oh, I see. So it would break things.
It would break backward compatibility, and the same thing goes for removing a field. If you remove a field that doesn't have a default value, older readers are still going to be expecting that field, and they'll run into problems.
Right. So default values are key.
Default values are your best friend when it comes to schema evolution.
Okay. So how does Avro handle null values in the data?
Avro is very explicit about nulls. It uses something called union types. So for example, if you want a field that can hold either a long integer or a null value, you would define its type as union null long.
Okay.
This way, there's no ambiguity. You're clearly stating that this field can be null, and you can only set null as the default value for a field if null is one of the types in that union definition.
Right. So everything's very clear and upfront.
Exactly. It helps avoid those nasty null pointer exceptions and makes the schema much easier to understand.
What about changing the data type of a field?
You can change data types, but there's a caveat. Avro has to be able to convert between the old type and the new type in a way that makes sense.
Okay, so it can't be just any random conversion.
Right, it has to be a logical conversion.
Right.
For example, if you change a field from a long to an int, that might be okay as long as all the values you're storing can fit within the range of an int. But if you try to change a field from a string to an int, that's probably going to cause issues unless you have a very specific way to convert between those types.
Yeah, that makes sense. What about if we just want to rename a field in our schema?
That's a tricky one. Renaming a field directly would actually break both backward and forward compatibility because Avro relies on those field names to match things up.
Right.
But Avro has a clever way to handle this. You can use aliases in the reader's schema.
Aliases?
Yeah, so let's say you have a reader that's using the newer schema with the new field name. You can add an alias in that schema that points back to the old field name from the writer schema.
Well, that's interesting.
This way, the reader can still understand the data that was written with the old schema, so renaming becomes backward compatible.
Backward compatible?
But older readers won't know about the new name, so it's not forward compatible.
Right. So aliases are like a bridge between the old and the new names.
Exactly. They help smooth the transition.
You mentioned earlier a rule about union types. What happens if we add a new type to an existing union?
Adding a new type to a union is backward compatible. Older readers won't see the new type, so they'll just keep working with the types they know.
Okay.
But it's not forward compatible. If a newer writer starts using that new type, older readers won't know what to do with it, and that could cause problems.
So it's a one-way street.
Kind of like that.
Okay, so we've talked a lot about writer schemas and reader schemas.
Yeah.
But how does the reader actually get the writer's schema? It can't just guess right.
It would be nice, but no, it can't guess. There are a few different ways this is usually handled, and it really depends on how you're using Avro.
Okay.
So for large files, like you might find in a data lake using Hadoop, where you have tons of records all written with the same schema, the writer schema is usually included right at the beginning of the file. Avro has a specific file format called an object container file that's made for this.
So the schema is right there with the data.
It travels together. It makes processing those big data sets much easier.
What about in databases or message queues, where you might have individual records coming in at different times, potentially with different schemas?
In those cases, a common approach is to include a version number with each record. And then you have a central registry, a schema registry, that stores all the different schema versions.
Okay.
So when a reader gets a record, it first checks the version number, and then it fetches the matching schema from the registry.
I see. So it uses the version number as a key to look up the right schema.
Exactly. And once it has the schema, it can decode the rest of the record.
That's a really flexible way to handle schemas that might be changing frequently.
Absolutely. It gives you a lot of agility.
What about when two applications are talking to each other directly over a network?
For network communication, especially with protocols like Avro RPC, the schemas are usually negotiated when the client and server first connect.
Okay.
So they agree on a specific schema version to use, and then all the data that they exchange after that will use that agreed upon schema.
So they establish a common language up front.
Exactly. It keeps things synchronized.
You also mentioned the idea of a schema registry earlier. Can you talk more about why that's so important in a more complex system?
A schema registry is like the central hub for all your Avro schemas. It's where you store and manage all the different versions. It's not just about retrieving the correct schema for decoding, though it also gives you this crucial ability to check if different schema versions are compatible.
Oh, that's huge.
It is, right? It's like a safety net. It helps you avoid those data integration headaches by making sure that any changes you make to your schemas follow those compatibility rules we talked about.
So it helps you prevent those oh no moments.
Exactly. Those moments where you realize you've broken something and you have to scramble to fix it.
And how does the schema registry keep track of all these versions?
It can use a simple incrementing integer for the version number, or sometimes it might use a hash of the schema itself, which is a more robust way to make sure the schema hasn't been tampered with.
So it can be either simple or more secure, depending on what you need. This whole schema-centric design of Avro seems like it has some real advantages over other binary serialization formats that maybe don't focus so much on schemas.
It definitely does. One of the biggest advantages is how well Avro handles situations where schemas are being generated on the fly. You know, like if you need to pull data from a relational database and turn it into a binary format.
Okay.
Avro makes it really easy to automatically generate an Avro schema straight from the database schema. Each table can become an Avro record, and the column names map directly to field names. It's a natural fit.
That's way more convenient than having to manually define field tags and manage them as your database changes,
Yeah.
which is what you have to do with some other formats, right?
Yeah, exactly. With things like protocol buffers or thrift, when your database structure evolves, you have to manually keep track of those field tags or field numbers and make sure everything stays compatible. It can be a real pain.
It sounds like it.
But Avro's design, because it relies on names instead of these explicit tag numbers, it's way more adaptable to dynamically generated schemas. And this can be a lifesaver in data integration scenarios. It saves you a ton of time and headaches.
Makes sense. And you also mentioned that code generation is optional in Avro. How is that beneficial?
Yeah, so unlike protocol buffers or thrift, which usually make you generate language-specific code classes from your schemas, Avro doesn't force you to do that. It gives you the choice.
So it's more flexible.
Exactly. It can work with statically typed languages like Java or C++, where generating code can give you some nice type safety and performance benefits.
Right.
But it can also work with dynamically typed languages like Python or JavaScript, where you might not want or need to generate code. You can just work with the Avro data directly at runtime using the schema.
So it adapts to different programming styles and workflows.
Exactly. It's very versatile.
You also mentioned earlier that Avro files are self-describing.
Yeah.
What does that actually mean for someone who's working with the data?
So because the writer's schema is embedded directly in Avro's object container files, those files become self-contained units of information. Anyone who has an Avro library can open up one of these files and immediately see the structure and the types of data inside without needing a separate schema file.
So it's like a little package with everything you need.
Exactly. It's all right there. This makes it super easy to explore the data, debug things, and process it, especially in tools like Apache Pig or Apache Spark that are designed to work with self-describing data.
That's a really nice feature.
Yeah.
So to recap, we've covered Avro's compact binary, encoding its reliance on schemas and its impressive abilities to handle schema evolution and keep different systems compatible.
That's a great summary.
This has been a really deep dive into Avro. I feel like I've learned a lot.
Me too.
For anyone out there getting ready for technical interviews, especially for those senior level roles, understanding these core Avro concepts is a huge plus. Interviewers want to see that you've thought about data serialization, how you've handled changing data models, and that you understand the trade-offs involved in different approaches.
Being able to talk about Avro intelligently shows that you've got a good grasp of these important technical concepts.
Absolutely. So as you continue preparing for interviews and exploring data serialization technologies, here's something to ponder. Avro is all about flexibility and schema evolution, and it often relies on a schema registry in more complex systems. So in what types of systems do you think Avro would be the perfect fit? And on the flip side, where might other encoding formats be a better choice?
It's a great question.
Think about that as you dive deeper into these technologies. Thanks for joining us on this deep dive into Avro.
Thanks for having me.
It's been a pleasure.
Likewise.
All right, until next time.
See ya.